Imagine you're taking a comfortable shower and someone flushes a nearby toilet. Suddenly, the water pressure drops and you're hit with scalding water. In industrial process control, the same crosstalk happens. If you adjust a continuous stirred tank reactor's feed flow rate to fix the product concentration, you'll often inadvertently alter the reactor's internal temperature. This is a 2x2 multivariable block diagram. The main forward paths, G11 and G22, represent our control objectives, specific inputs managing intended outputs. But interacting crosspaths act like that toilet flush. They carry disruptive signals bleeding into other loops, making the system harder to stabilize. Mapping these variables onto this diagram is the necessary first step to isolating these crosspath effects and reclaiming independent control over each loop. Before we calculate how to cancel those interactions, we need to pair our variables correctly using the relative gain array, or RGA. To minimize natural interaction, choose the pairing where your lambda value is closest to 1. If lambda is 0 or greater than 1, the loops fight each other. At exactly 0.5, you reach maximum interaction, where both inputs affect both outputs equally. Correctly identifying these values ensures you aren't trying to control a system that is fundamentally unstable from the start. Once the variables are paired, we introduce cross-controllers, or decouplers, to mathematically cancel out the remaining crosstalk. Look at the subscripts to track the signals. Elements ending in 11 or 22 are your primary controllers, while crosspath elements ending in 12 or 21 represent the decouplers. We derive the decouplers by forcing off-diagonal matrix elements to 0, solving for the specific cross-controller GC12. Pay close attention to the negative sign at the front of this formula. The decoupler must subtract the interacting signal to neutralize it. This derived equation provides the exact mathematical structure required to build a fully decoupled control system. Let's apply this. Here are the plant parameters and transfer functions for a typical multivariable system in example 12.3. Pause the video here. Substitute these specific values into our GC12 formula and solve for the final expression. As you simplify the terms, they cancel out to leave negative 2k2 over s plus 5. Performing this exact substitution is the specific skill needed to resolve decoupler values on an exam. The true test of this math is how it changes the physical behavior of plant outputs. This first graph shows a system without decoupling. A set point change causes both outputs to fluctuate significantly before settling. The second graph shows the result of cross-controllers. Output 1 reaches its target smoothly, while output 2 remains a perfectly flat line, completely undisturbed. The algebra we performed in the previous act is what physically forces the plant to behave with this level of isolated precision. Here are the two most important rules for your revision. On the left, pair variables where lambda is closest to 1. On the right, remember every decoupling formula must lead with a negative sign. Take a screenshot as your final study reference. By combining RGA pairing with these decoupling formulas, you can now systematically isolate and control interacting loops in a 2x2 MIMO environment.